Okay, grade 12s. So some of you have been asking me questions, and I'm sorry, I actually forgot to answer them. I've been so busy with everything else this week, and I have to working on like report cards. But don't worry, your report card marks, I'm submitting some tomorrow, but I'm going to change your mark for before they print them to include the last test. All right. All right. So. Yeah, some of you have been asking me some questions. Yeah, okay. Can I just tell you that it's nice if you guys, when you're asking questions, if you can do it a little bit at a time and not ask, like, let's say 10 questions in one shot, but just a little bit by bit is easier. And since a lot of you are having questions on the thin film interference, I thought I would help you with that right now. So this is page 519, number 3. Okay, what is the minimum thickness of air layer between two flat glass panes if the glass is to appear bright when 450 nanometer light is used? You can ignore this 90 degrees business. It's always like 90 degrees, so anyway, it has to be like pretty much coming straight down. If the glass is to appear dark, okay, and it says use a diagram to justify your reasoning. All right, well, here's my diagram. Glass, glass, air. Okay, so this is going to be, sorry, not inverted, because that's a soft boundary between the glass and the air. And I know I drew this diagram for you. I wish you guys would look at my notes. This one is inverted. Alright, so like here, we'll just use our check mark system. So this one is not inverted, this one is inverted, okay? Now that means these two rays are out of phase to start with. And so step 1 is from the diagram here. So ray 1 is an X, okay, ray 2 bounces off a hard boundary there on the glass on the bottom, so that's a check. So that means they are out of phase. You have to do this step. Some of you are asking me, like, how do I know which to start with in the next step? And it's like, well, if you don't do step 1, how do you know what to do in step 2? You're absolutely right. You got to do step 1. Now that they're out of phase, that means if the path difference is 0, they're going to get destructive interference. If the path difference is a whole wavelength, again destructive. 2 whole wavelengths, destructive, and so on. Okay. We don't have to change the wavelength, so we can skip all the way to step 3. Or, you know what? I'll write step 2 just to make you happy, because I know this makes you happy. The wavelength in the medium will equal the wavelength in the vacuum divided by the index of refraction for air. So that's just the wavelength in the vacuum divided by 1.0. So in other words, it's just the same as the wavelength in the vacuum. So we don't have to change it. The wavelength in the vacuum is 450 nanometers, and we do not have to change that number. All right, now we'll do step 3. So step 2 is a trivial step. We just have to realize the wavelength doesn't really change in the air. Okay, now step 3. Step 3, you have to do your cases. Now, we are looking for bright, okay? And we're looking for the thickness, that's T, okay, there. So bright means constructive interference. Bright means constructive, which I think you would get that, okay? And our first case of constructive interference is when the path difference equals 1/2 of a wavelength. Now, how do I know that? Okay, how do I know that? The thing is, I know that because of step 1. Okay, because the waves are out of phase, I have to put them back. They're out of phase by 1/2 of a wavelength. Okay, so if you're a source of waves and you're emitting a crest, whenever I'm emitting a trough, we're half a wave out of step. So to shift them back into step to get constructive interference, you have to shift them by half a wavelength. Okay? If they were in phase in step 1, then to get constructive interference, I would have a full wavelength, not half. Okay, and that's how you make that decision. Okay, so path difference is half of a wavelength equals twice the thickness. Now, 2t, here I'll just solve it for t. Let's pretend we're math geniuses. Oh, what am I doing? Let's pretend we're math geniuses. This would be 1/4 of the wavelength then. So I just have to take 450 and divide by 4. What is that? 112, right? 0.5, 450 divided by 4. 450 divided by 4. 112.5. I'm a genius. There you go. Nanometers. Okay, that's it. Now in B, step 1 is the same. So I don't have to redo step 1. Let's go straight to step 3. Step 1 and 2, these two steps are the same. So let's go straight to step 3. And then here we're looking for destructive interference. Now that will happen at 0 because they're out of step. But we're looking for a non-zero thickness, I'm assuming. Minimum thickness, well, we're not going to go with 0. We'll take the next non-zero one would be when the path difference equals a full wavelength. And how do I know that? It's because they're out of phase. So they're already producing destructive interference with 0 path difference because they're out of step in step 1. So now, if I shift them over by a full wave, they're still out of step because they both shifted over by a full wavelength. They're still out of step. So therefore, when 2t equals a wavelength, okay, and t equals the wavelength divided by 2, that's 450 divided by 2. That one's easy, you math geniuses out there, 225 nanometers. So that's how you do questions like that with the glass. Okay, it's just like a thin film question. We do it the same way. The only difference is you have glass, air, glass, and that's it. All right, this question here, a Plano convex lens, flat on one side, convex on the other. This is like Newton ring apparatus. The dark spot is observed in the center, okay, surrounded by 15 concentric dark rings, okay, with bright rings in between. How much thicker is the airwave to the position of the 16th dark ring than at the center? Well, the center is where the path difference is 0, by the way. But here's the deal with this. Again, like you've got this glass like this, okay, glass like this. At the center of the path, they're touching, so the path difference is 0, okay. But again, you're going to have glass, air, and glass. Okay, and again, it's just like the last question. This ray is going to be inverted, but that ray is not. Or sorry, I got it backwards. This one is not inverted, that one is. So that the second one is bouncing off a hard boundary of glass. The first one's bouncing off air. That's a soft boundary. Okay, so they are step 1. They're out of phase. Okay, step 2. Let's just get straight to it. It's the same as the last question that we just did. The wavelength equals the wavelength in the vacuum. So it's divided by 1.0. Okay, what color? 521 nanometers. So that means this is just, I'm sorry, that looks like a weird number. 1.0. That's 500 nanometers. Okay, so that's all good. Step 3. All right, so now we're going to look at case by case. Now we're looking for dark rings. Okay, dark means destructive interference. We're looking for destructive interference. Okay, and that will happen when the path difference is, since they're out of phase, 0, a wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths, and so on. In general, it's equal to n wavelengths. Okay, if that makes sense to you, like it's just the first one's 0, and then so on. Okay, now let's do it. The center. It says the center dark ring, there the path difference would equal approximately 0, so therefore 2t equals 0, and the thickness is approximately equal to 0. Okay, so that's at the center. Now at the 15th ring, okay, at the 15th ring, the 16th position of the I guess they count the center one as a ring. It's really a circle, but anyway, they count it as a dark spot. They're counting that as one of the rings, and then the 15 other rings for the 16th dark ring. So now what we're going to do is we're going to say that the path difference I think they would do it this way on the 15th ring. 15th, if they count 0 as your center one, then the 16th one would be the 15th ring. It's kind of weird because the dark spot is not a ring, but it's counting as a ring in this case. So dark spot is 1, and then the 15 rings outside of it would be, you know, the next 15. But there's a total of 16 things, including 0, right? So we're going to go with that. So 2t equals 15 lambda, right? T will equal 7.5 wavelengths then. Now we just go ahead, plug in your wavelength. So just plug in 500. So it'll be 7.5 times 500. That's 3750 nanometers. So how much thicker is it? This is your answer. Because the other one's 0, so it's the 15th ring would be 3750 nanometers. Okay, next. Okay, and guys, like on a question like this, if you watch my videos and following along, and you need to read and practice the method too. Okay, that's part of it. Like so, like I give you the method in steps, step 1, 2, 3, 4. Now your job is to read it, follow it. Okay, some of those questions, like the last question is a little unusual, so I get why you need help there. This one here, though, just follow the steps. Okay, so look, you've got a layer of magnesium fluoride on flint glass. Okay, now there's always air. Okay, so it's like this. You have air. You have your magnesium layer here. So air is 1.0, that's air. Here's your little layer, okay, your thin film. That's N equals 1.38. And then on the bottom here, I'll use a different color. Here's your glass block. Is your lens system, whatever it is. That's N equals 1.66. Okay. Now if I draw my ray, oh, I'm sorry. I reflect off the wrong spot. Okay. If I draw my rays, the one that bounces off the top will definitely be inverted. That's a hard boundary, right? It's in air, and it's bouncing off of something more solid than air, right? That thin film. Now the next ray will penetrate through, and it will bounce off, and it will be inverted too, because the glass is more dense than the thin film in this case. So that's another hard boundary. So there's 2 hard boundary reflections there. So that means they're in phase. Okay? So this is unlike the question we just did. All right, so that's step 1. Okay, now it says we want destructive interference. Because they're in phase, we have to make them out of phase. So it says the minimum thickness. So what we want is to undergo destructive interference. That's right. Okay, so step 2. We need the wavelength in the medium equals the wavelength in a vacuum divided by 1.38. This is our medium, that's our thin film, right? So don't use 1.66, that's not right. So it's 550 divided by 1.38. And that is 398.6 nanometers. 398.6 nanometers. Okay, so that is your wavelength in the medium. And now we go ahead and do step 3. Now, guys, step 3, I'm looking for destructive interference. Destructive interference, right? Okay, so what will give me destructive interference? The first path difference to do that will be half of a wavelength. Now, why is it half of a wavelength? Well, because of step 1. They're both in phase, right? So they're in phase, they're in step with each other. I need to get destructive interference, I need to shift one of those waves by half of a wavelength. So we're looking for destructive interference. Okay, in order to do that, I need to shift by half of a wavelength. So 2t. Remember, the thickness of the film is t. So 2t equals 1/2 of a wavelength. T equals 1/4 of the wavelength then. Now, it's 1/4 of the wavelength in the medium. So that will be the number that we just got divided by 4. I get 99.6 nanometers. 99.6 nanometers. And that, my friends, is how you do thin film and air block questions. It's not really an air wedge. Air wedges, you'll know that'll say a wedge, okay, and not just one piece of glass lying on top of another one. So that's it, guys, and please follow the steps, okay, those 3 steps to do the thin film questions. It's not just one formula that you can use, okay. So that's it for now, and we'll talk to you soon.